So this now is a situation where we have non-zero acceleration, first time here. So what I'm going to do is I'm going to put the man at minus 10 at time 0, and I'm going to have his initial velocity be 0, so initially he's not moving. And the acceleration now is 0.5 meters per second. So over here, to explain a little bit more precisely what I mean by acceleration, I have in these blue numbers I've made a table, and this leftmost column is time in seconds. The next column is instantaneous velocity, and so this would be, well, in terms of speed, it would be what a speedometer would read in terms of meters per second. So imagine that we had a speedometer calibrated in meters per second and that we were moving to the right, which tallies with the positive velocities you see here. That's going to be going in that direction, to the right. And so what I've put together here is a situation where the man starts at time 0, he is at minus 10, and his velocity initially at time 0 is 0 meters per second. But then in every second, his velocity increases by 0.5. And so you can see him going, at time 0 he's going 0 meters per second, but at time 1 second he's going at 0.5 seconds. And at time 2 seconds he's going at 1.0 meters per second. And at time 3 seconds he's going at 1.5 meters per second. And in every subsequent 1 second, his velocity increases by plus 0.5 meters per second. So we're going to go through this in detail, but the big picture is if you look up here at the motion diagram with the delta t of 1 second corresponding to what I'm using in this table. So the first interval is just this little tiny little bit, when we'll talk about exactly how much that is. And then the next second he goes a little bit further because his velocity is increasing. And in the subsequent second, at t equals 3 actually, he goes further, and then second number 4 he goes yet again further, and then second number 5 yet further again, 6 further again. And so the big picture here in terms of the motion diagram is this sequence of displacements which get larger and larger, rightward displacements, which get larger and larger corresponding to the fact that his velocity velocity is getting more and more positive. Okay, so now let's actually do this, and I'm going to let him go and try and stop him before he hits the wall, but I probably am not going to succeed in doing that. So you can see I've set this now, so he is x naught is at 10 minus 10 meters per second. That corresponds to him being at minus 10 at 0. 0 velocity initially, but this now is going to change over time according to this, and the acceleration is now 0.5. So the significance of the acceleration is it's the amount by which the velocity changes every second. And since we're only interested in constant acceleration in this course, this is a constant amount. Okay, so let me go ahead and run this, and you'll see what happens. So here he goes. His velocity is increasing. You can see this getting bigger and bigger. And I'm going to stop him as close as I can to the other end. Okay, so he's gone for pretty much 9 seconds, just a little bit shy of hitting the wall here. And you can see at 9 seconds he will have gone the full 20 meters. He'll be at position 10. Okay, so let's now walk through this table here and understand how this all comes about. So the starting premise is that he starts with 0 meters per second instantaneous velocity, so that's the term we're going to use here, at position minus 10, and in every subsequent second his velocity increases by 0.5 corresponding to this acceleration. So in other words, the change in velocity per unit time is 0.5 meters per second. In other words, it's 0.5 meters per second squared. So look at this first time interval. From time 0 to time 1, He starts at 0 meters per second, and 1 second later he's going at 0.5 meters per second. So that means that his average velocity is halfway in between these two numbers. Well, that would make it 0.25. Well, if his average velocity over this 1 second time interval is 0.25 meters per second, it means he's gone 0.25 meters during that 1 second. And so therefore, from time 0 to time 1, he's gone from minus 10 to minus 9.75. He's gone 0.25 meters to the right. Then for the next second, his velocity, instantaneous velocity, starts at 0.5, and at the end of that second, at time t equals 2 in other words, he has a 1.0 meter per second. The average between these two numbers is 0.75. So you can see the difference of 0.5 between these two. Well, if over this 1 second time interval his average velocity is 0.75, that means he's gone 0.75. Average velocity 0.75 meters per second. That means that his displacement is 0.75, which means that he's gone from minus 9.75 to 9.0. And that corresponds to this t equals 2 being at this position. And so what you see is we can walk through this whole table and continue to find what the average velocity is in every single case. And so let's just jump down here, for example. So this from second 5 to second 6, his average velocity is 2.75, halfway between 2.5 and 3, which means his displacement is 2.75, which means he goes from minus 3.75 to minus 1.0. And so it goes. And so that's the picture. And now I want to show you this in chart form. So let's go over to chart. And let's use the same settings here. So I'm going to go minus 10, starting velocity of 0, and we're going to use a 0.5 meter per second acceleration. And so now I want you to look at the curves that get generated here. Okay, so here we go. Just making sure I have everything set up correctly. Oh, hang on a sec. Let's start that again, because I want them to start at minus 10. Minus 10 and 0.5. Okay, I think that's let's see. Okay, so what I'm trying to do is change the scales here, so these are a little bit more, so you can actually see what's happening. So let's see if I can do this. Yeah, so you'll be able to see a little bit better what's going on here. Okay, and then this one is probably okay. Okay, so let's go with that. Okay, so now you see the velocity is increasing at a steady rate. The slope of this velocity is the acceleration rate here. Well, he hit the wall at roughly t equals 0.9. You can see that's consistent with our chart here. Okay, so here's the big picture here. So this is the 0.5 meters per second, and the slope of this, the slope of the velocity versus time curve, is 0.5. And then this now goes up in a nonlinear fashion. This goes up when you have acceleration. You have this increasing Well, the math word is quadratically, as a t squared kind of a thing. I think that's a really good example for positive acceleration. And what I want to do in the next one is to show you what happens if you have a starting positive velocity and you have negative acceleration.